Hello everybody. Today we're going to be talking about frequency modulation, otherwise known as FM. It's at this point the most widely used transmission modulation scheme on the planet, and we'll see why in a moment, the advantages of FM are. Our lab this week, we do make a FM modulator. And you'll see some of the waveforms that you should be expecting here in this presentation. So what we're going to talk about is some of the principles of FM, frequency modulation, the principles of phase modulation, which is very similar. It's almost difficult to distinguish the two. Just like with AM, there's a modulation and there are index and sidebands associated with FM also. We'll see how FM has better noise suppression characteristics than AM, or I should more accurately say immunity to noise. And then we'll look at the differences between FM and AM. So just like AM, okay, you take a sine wave, you can vary in that sine wave, you can vary the amplitude, you can vary the frequency, and you can vary the phase. The only other variable in the sine wave formula is t, which is time, and you can't change that, unfortunately. If we could, we'd be in good shape. But the other three things we can change, and today we're going to talk about changing the frequency, and we're going to talk a little bit about changing the phase. Those are two different modulation schemes, but again, they're very, very similar. Now, one thing to keep in mind with FM, the carrier amplitude is constant. The FM receiver doesn't really care that much about the amplitude. There's got to be enough meat on the bone to get the signal there, but it's pretty much impervious to changes in amplitude. Matter of fact, it tends to just clip it or limit it. And so any variations in amplitude really don't make that much of a difference in an FM receiver. Only the frequency does. That's the only thing it cares about. Frequency and to some extent the phase, which we'll see. So the way FM works is that you have a carrier at a resting frequency. So it's a particular, let's say 100 megahertz. And as you increase the amplitude of the modulating signal, it moves that resting frequency higher. And then if you lower the amplitude of the modulation frequency, it moves the resting frequency lower. Okay? So as the modulation goes above and below zero, you get this breathing, if you will, a modulation of the resting frequency, which is basically the carrier frequency. That's the frequency you tune to on your FM dial. So if you tune to 103 megahertz on your FM dial, that's the resting frequency. So there's this frequency deviation. That's the amount of change in the carrier frequency produced by the modulating signal. Now, the higher the amplitude of that modulating frequency, the greater that deviation is going to be. Okay. Now, how fast does it deviate? Well, it all depends on the frequency of the modulation frequency. So if you have a modulation frequency that is really fast, you're going to see this frequency deviation bounce back and forth very quickly. All right. But if the modulation frequency is very low, you're going to see that frequency deviation move very slowly. So there's a one-to-one correlation between that. So you have frequency deviation and you have the frequency deviation rate. So here's an example of the modulation signal. It's 500 hertz. The carrier shifts above and below the center frequency 500 times per second. So the frequency of the modulation signal determines that frequency deviation rate. And again, the amplitude determines how far the deviation goes, how far away from the resting frequency the actual carrier is deviated. So here's an example. Transmitter operates on a frequency of 915 megahertz. That's a coincidence because that was when I did radar many years ago. That was the frequency we used. That's part of the industrial, scientific, and medical spectrum, which is open to everybody to use. And so it's a very common frequency area. That 900 some odd, 915 seems to be a favorite one. Also up at 2.4 gigahertz. That's another part of the ISM band, just so you know. So 915 megahertz, maximum deviation is 12.5 kilohertz. What are the maximum and minimum frequencies that occur during modulation? Pretty straightforward. 915 megahertz. You add 12.5 kilohertz to it. You get 915.915.012.5. And then the minimum deviation, the lowest frequency is 914.987.5. So it's a simple arithmetic operation, not too many fancy formulas here. So here's some waveforms. This is what you're going to see in your lab. All right, so what you're going to do is use two channels of the scope. Channel 1 is your modulation signal right here. All right, this is the resting frequency up here on the top. So this is what's coming out of your 2206 modulator, okay? And here's the modulation, and when you apply that modulation to the carrier, you get these changing frequencies. See, this is modulating to a lower frequency, and it modulates up to a higher frequency. One thing that's important to note here is that your 2206 device in the lab has an inverse transfer function, meaning that when the amplitude comes down, you're going to get a faster frequency, higher frequency. When it goes up, you're going to get a slower frequency. It doesn't matter. It's going to sound the same in your speaker if you have it hooked up to if you're using it as an FM receiver. It doesn't make it, just the phase is the opposite. This down here is and this is kind of impossible to draw. They tried, but check it out. It's pretty much the same as the FM signal, this phase modulation. It's just shifted. Okay, so here it's really responding to the rate of change. So right here we're getting a rising edge, you're getting a shift in frequency. It basically moves the entire waveform back and forth. All right. Now what's interesting, I think, is that the device at the other end, the receiving device, this is the transmitting waveforms, the receiving device, the demodulating circuitry, it's oftentimes a phase lock loop, okay? And in fact, we're going to build a phase lock loop in our lab, and we're going to see how your modulation circuit, which you're building in the lab, is going to be demodulated by the phase lock loop. So leave room on your breadboard for the phase lock loop part, and do not disassemble the modulator, the FM modulator, because we're going to use that again, just like we did with the AM stuff. But what's interesting, I think, is that the phase lock loop that demodulates the FM signal, whether you're doing a FM modulation or a PM modulation, either frequency modulation or phase modulation, the phase lock loop doesn't care. It works the same way either way. It'll demodulate both of them. So it doesn't know the difference. And it's that's one good thing about this diagram, is if you look at both of them, they look the same, right? So a phase lock loop receiver receiving this waveform, which is FM, versus this waveform, which is PM, it doesn't know the difference between the two. And in fact, you can't tell the difference unless they're right next to each other, and you see that there's just a slight, literally a phase shift for the PM. Okay, so sidebands. Anytime you modulate something, as we saw with the spectrum analyzer demonstration, and we also saw with that some of the other demonstrations, you see it with your labs. You always get sidebands. Okay. Now the difference between AM sidebands and FM sidebands, AM sidebands, as we know, we get two side frequencies. So this statement here, when a constant frequency sine wave modulates a carrier, two side frequencies are produced. That's true for AM. Okay, for FM, it's 2, but there's many, many more. There is literally an infinite number of them. Now, they die out very quickly, all right? So you won't see them after a couple of significant sidebands, which we'll talk about in a minute. But they are a lot of sidebands. So it's much wider bandwidth than an AM signal. Okay, so the bandwidth of an FM signal is much wider than that AM signal with the same modulating signal because of all those additional sidebands. Okay, so modulation index is a ratio for FM, ratio of frequency deviation to the modulating frequency. Okay, most communication systems using FM, the maximum limits are put on frequency deviation and modulating frequency. So what if you had 100 megahertz carrier, right? And you wanted to modulate that with a megahertz. Well, you'd get 101 megahertz, and then you get 1 megahertz minus. I mean, I'm sorry, 100 megahertz minus a megahertz. So that's a pretty wide bandwidth. That's 2 megahertz at least, plus all the other sidebands that come along with it. You can't do that and maintain preserve spectrum. So in broadcast, in FM broadcasting for your listening to your radio, the maximum permitted frequency deviation is 75 kilohertz. Okay, so that's the maximum amplitude representation, if you will, of your carrier deviation is 75 kilohertz. That's the furthest away from the carrier you're going to get. So at that 100 megahertz example I just gave you, I said it'd be a 1 megahertz modulation. Forget it. It's nowhere near that. It's only 75 kilohertz. That's the most they allow. Now, the maximum permitted modulation frequency is 15 kilohertz. Okay, so that's the fastest that deviation is going to happen. Well, think about that. You know, our hearing, supposedly, not mine, but some of us anyway, still have 20 to 20 hearing, 20 hertz to 20 kilohertz. Well, the FM band limits it to 15 kilohertz, so you're chopping out the top 5 kilohertz. Not uncommon for a lot of what we listen to these days. Compressed audio, very similar scheme. They save bandwidth, they save bit rate for your streaming devices by chopping off the top 5 kilohertz. So most of us can't hear that anyway. I know I can't. Haven't been for a long time. Modulation index for standard FM broadcasting is therefore 5, but 75 kilohertz divided by 15 kilohertz. Okay. So Bessel functions. Oh, sounds scary. This is a set of equations that express the phase angle in terms of sine wave modulating signal, but you have to use a complex mathematical process known as Bessel functions. Now, good news, that's the bad news. The good news is that we don't have to do any Bessel functions because they're all published in tables in terms of coefficients. So here's a Bessel function table. On an exam, you will be provided with this, or you will be allowed to look at a Bessel function table. This title up here should say sideband pairs. So carrier and sideband amplitudes for different modulation index. So here's the first set of sidebands, second set of sidebands, third and fourth, and these are the relative amplitudes of them, okay? So if you look at the different modulation indexes, you have, so as you increase your modulation index, see there's more sidebands. That's the lesson here, I guess. And you can actually calculate them. So if I ask you, all right, so for modulation index of 4.0, what are the relative magnitudes of the first and second sidebands? And your answer would be minus 0.07 and 0.36. Okay, if you want to keep going, you can go all the way down here to the seventh sideband. Now notice that some of these sidebands are more significant than others, meaning they're bigger than others. Okay. Here's a plot of that data. Look at that. So, little mathematical symbol here. The exclamation point means a factorial. Tells you to multiply all the numbers for which the symbol is attached. So 5 factorial means 1 times 2 times 3 times 4 times 5 equals 120, which we use that in solving Bessel functions, which we're not really going to cover here because really all we're going to do is use this table every single time. There are examples of this in the text and also a couple homework problems that you need to do and it's really all you do is you get the modulation index and then you write down these numbers here going across. So it's not too bad. Narrowband FM is the most common FM system that we have, that we use, and that's a modulation index which is less than pi over 2 or 1.57. It conserves spectrum space, a little more signal to noise ratio, but not that much. So that's how we can fit all those stations on the FM band, okay, that we have, which goes from about 88 up to I think 107 megahertz, roughly, for our FM broadcast band. So again, higher the modulation index, a greater number of significant sidebands, and a wider the bandwidth of the signal. In order to conserve spectrum, we reduce the modulation index. Here's an example. So we have a modulation index of 6 kilohertz divided by 3, because the deviation is 6 kilohertz, the modulation frequency is 3, so the modulation index is 2. The bandwidth is 2. FM, which is the modulation frequency, times N. N is the number of significant sidebands, okay? So the significant sidebands is 4. Where do we get that? We got that from the Bessel table. It shows that there's 4 significant sidebands when you have that modulation index of 2. So significant sidebands are those that have an amplitude greater than 1% in the Bessel table. So let's talk about noise, one of my favorite subjects. Not really, but I think a lot of my life is taken up by fixing noise problems on circuit boards. So it's an interference that interferes with the signal that you want, okay, generated by lightning, motors, automotive ignition systems, and power line switching, and all sorts of things. It's also generated by your own circuit. So you can get parts of your circuit generating noise into other parts of the circuit. So you can shoot yourself in the foot, so to speak. Transient noise are narrow spikes of voltage, very high frequencies. They come and go. And noise is typically a voltage phenomenon. In other words, it adds to the amplitude or subtracts from the amplitude of the carrier in a broadcast signal, okay? Sometimes it'll completely wipe out the signal, and that's not good, obviously. But remember what we said at the very beginning of this presentation. FM doesn't really care about amplitude. So when noise comes along, it's a lot less susceptible, or does a little more immune to that noise, okay? So it's a constant modulated carrier amplitude, doesn't really care about the noise. The receivers actually contain limiter circuits that restrict the amplitude, so if you get amplitude variations, it's not even going to see it, okay? So here's a little diagram. Here's some noise right there and some noise right there. The receiver doesn't see it because it's clipping the amplitude right there. Now, I want to stop here and explain something else about noise when it comes to FM. Remember, the phase lock loop or the receiving device is taking the frequency or the phase of the FM signal and using that in the demodulation process. So even though noise comes along and changes the amplitude, it doesn't care because the phase or the frequency of the signal doesn't change. Except for one condition. look at it right here. See this noise spike right here? If that noise spike happens right at the zero crossing, all right, then it might cause the receiving device, the phase lock loop, to interpret that as a phase change. And what happens? It outputs a static, a brief transient static. So message to you is the worst possible place for noise to occur is right there, right where it crosses zero, because that's the spot that the phase detector on the phase lock loop uses to determine the phase of the signal. So if noise is going to come along, no, don't have it happen there. Have it happen over here at the peaks or something. Also, there's something called coherent noise, basically noise that is in sync or in phase with the FM signal, the carrier, and it's repeating. So it's cyclical, all right? It's basically periodic. And if that period of the noise happens to match the carrier frequency, all right, what's going to happen? It's going to get hit every single time. And if that happens to line up with the zero crossing, your FM signal is going to really suffer. So FM is certainly more immune to noise than AM by an indescribable magnitude. All right, it's huge. That's why it sounds so quiet on your FM dial. But we've all heard noise on FM when we listen to it in our cars. It does happen. And a lot of times that is because of what's called coherent noise or synchronous noise, where it's synchronized somehow with the FM. And it could be a coincidence. The other thing is if you have two FM receivers next to each other, all right, there's called a local oscillator in the FM receiver. That, if that's not shielded properly, that will leak into your other receiver, and that can be interpreted or as coherent noise, okay, and mess with the FM receiver. So FM is not completely impervious to noise, but it's much better than AM, obviously. So you gotta have some, you know, the stars have to line up just right for it for you to hear noise in FM. So when noise does happen in FM, it normally affects the higher frequency components. Okay, so what we can do is emphasize those higher frequency components or higher frequencies in the modulation frequency. And the only way, the easy way to do that is to put a high pass filter on the modulation signal. And that's called pre-emphasis. And then what you do on the other end is, so here it is, there's a little high pass filter on the modulation input. And then you can use a low pass filter on the receiver, which is called de-emphasis, to put things back the way it is, the way they're supposed to be. And pre-emphasis and de-emphasis are used a lot in electronics. FM is one place, but it's also used on records, LP records, a long time ago, back in the 30s or 40s when records were first invented. These very smart mechanical and acoustic designers, these scientists, determined that the needle moving in the groove of the record needed to be compensated for, because high frequencies, for example, had to move the needle very quickly and low frequencies moved it slowly. So there was a non-linear characteristic to the mechanics that were going on with the needle. So what they did is they added basically a pre-emphasis, and it's not linear. It's not linear like this. It's called the RIAA equalization curve, Recording Industry Association of America, and you can look it up. It's very it's kind of a squirrely kind of curve, but these smart people back then determined that. But it's the same principle. Basically, you're compensating for a deficiency of your modulation signal, if you will, and then you de-emphasize it on the way out and put things back the way it was, the way they were. So here's the de-emphasis circuit. That's the other end of it. So that would be a low pass filter. So advantages of FM. Again, superior immunity to noise. As I mentioned, the receiving device is normally like a phase lock loop. We're going to do a couple other kinds of receivers in our lab, but it's very common is something that locks onto the phase. The circuit locks onto the phase of the incoming signal. And once it does that, it's captured it. Any other signals that are involved, it'll tend to ignore. Okay, so it's called capture effect. So that's pretty cool. I mean, that is a big benefit of FM. Whereas AM, you know, anything that comes in there, it'll pick it up. So again, this is another big noise suppression characteristic of FM. Oh, the other big thing about FM is that you can use Class C transmitters. Remember, Class C are either all the way on or all the way off, so they're very efficient. So they have constant amplitude. You don't have to use linear amplifiers like in AM, right, that have a varying amplitude on the output. You can go full on and full off on your transmitter, and it increases transmitter efficiency tremendously. So you can use a Class C. Now, disadvantages, not so sure about this. We use considerably more spectrum, that's for sure. That's definitely, all right? It does use more spectrum because of those significant sidebands. Second bullet, FM has more complex circuitry for modulation and demodulation. Third bullet says the second bullet's not really true. Okay, in the past, yeah, they were more complicated. But now we've got these fancy ICs that we just make, and it's so much easier, and they just put a part on there. They're inexpensive and easy to use. And FM and PM, phase modulation, become the most widely used modulation method because of that, because of the noise suppression effects. And they're not as expensive as they used to be. So it's pretty cool. And we have a little table here. I think this table is kind of neat. Here's some applications, different types of broadcasts. So obviously IM broadcast radio is AM, FM broadcast radio is FM. Stereo, FM stereo uses FM, plus on the sidebands, they pop a little AM on there to give you the stereo imaging. So they multiplex those two together. These next three are a little bit dated because we have digital TV now. This was the old ATSC, before the ATSC standards came out several years ago. But it used to be TV sound was FM, TV picture was AM, and vestigial sideband is what that's called, that stands for. And then the color signals were quadrature double sideband. None of that's really true anymore because we have digital TV, so it's a transport stream. Cellular telephone, which this is still true. We have FSK, PSK, and FM. We also have some other standards now that have emerged in the last few years. Cordless phone, anybody use those anymore? Fax machines, I don't think anybody uses those anymore. Aircraft radio, this is still true, it's AM. And marine radio is FM and SSB. CB is AM and SSB. CB, I heard, was moving to FM. Interesting. Amateur is FM and SSB. Modems. Nobody uses modems much anymore. Garage door opener is UUK. What does UUK mean? On-off keying. Okay, it's an amplitude scheme where the signal's on or off, and it's sort of like Morse code. All right. Except the carrier is always there, but you have an amplitude that's high and then an amplitude that's low. All right, so it's called ook, and same with the TV remote control. And these last two, I guess VCRs aren't around anymore, but family service radio, I guess that is. So that's it for today. If you have any questions, please post them in the discussion area on our Canvas site. Thank you.